Okay, so here we're told that the y-axis of our original graph is inches, and the x-axis is days, which is important to note, so that you've been told that those units are really, really important as you move forward. Okay, so always kind of taking note of what the units are. In any sort of word problem or, any problem with a context, that is really important. You always want to be thinking about what the units are, and then what are the units in your derivative. Okay, so here it wants to know what the graph in figure B represents. Basically, if you're being asked what a derivative represents, you should be writing that it's the rate of change of something. Here it would be the really a correct answer, fully correct answer would be the rate of change of the depth of water. Okay, that's what it is. So it's the change in whatever the y was before. So the y was the depth. Now the units would be what? What would the units be here? What would we measure y prime in? Y was measured in inches, but y prime won't be. Y prime should be a rate.
Inches per day.
It's inches per day. Okay, so it's always, because derivative is just slope. So derivative is slope, and slope is y over x, right? Change in y over change in x. So whatever the unit is in the y, that's what's going to go on top of your rate, and whatever the unit in the x was is going to go in the bottom. So here it was y over x, that would be inches per day. That's the thought process you should be using. Okay, so if you're given a graph that is position, and the y is kilometers and the x is hours, when you take the derivative of that, it gives you kilometers per hour. Okay, whatever it is. Even if you were given a velocity graph, so if you were given a graph where x was hours and then y was kilometers per hour, the derivative would be kilometers per hour per hour. It's always whatever the y is over whatever the x is. Okay, so here, I mean, there's no space for it, so obviously you can't be that verbal here, but what's happening in the ditch. So you would just be saying that at first it's filling up quite quickly, and it's good to use those words, like it's increasing more quickly at first, right? When we see it here, it's increasing very steeply. Ooh. Okay, it's increasing really steeply at the beginning, like over here, and then it's sort of slowing down. Okay, and it's still up, right? But the level is now going down, okay, until it starts to go up a little bit at the very end. Okay, so just describing that. Now, it wants to know when it's the wettest, when it's the driest. Wettest would be at x equals 2, it looks like, so day 2. Right, that's just when it's at a maximum. Okay. And the lowest point looks like it's at 6. Okay, or at 0. Yeah, it looks like it's a 0 too, right? So, and that's important to note because 2 and 6 have an interesting feature. 2, what happens at 2 on the derivative? It's at a 0. Thank you, Haley. And what happens at 6? It's a 0. So what could we probably say about zeros of a derivative function?
There's no maximum.
They're at a maximum and a minimum. Okay, it's saying the rate of change is 0. That's what it means. Okay, the rate of change is going to be 0 at a maximum or minimum. Think about it logically, like we've talked about, right? If the derivative is positive, the graph is going up, right? That's increasing. If the derivative is negative, the graph is decreasing, it's going down. If you have a situation where you're going from increasing to decreasing, so it's going from positive to negative, in between those two things, you're going to have a 0. Because to go from positive to negative, you have to pass through 0. And if you think about a graph, when it's going from increasing to decreasing, that's what creates that maximum. Or if it goes from decreasing to increasing, that's what creates a minimum. So if I look at just the derivative graph, if I didn't even give you the other graph, if I just gave you this graph here, if I know the zeros are minimums and maximums, they're what we call local minimums or maximums, or relative minimums and maximums. How could I tell looking at this? I know 2 is either a minimum or a maximum, and I know 6 is either a minimum or a maximum. How can I tell which is which if I was just looking at the picture of the derivative?
One's going down, one's going up.
Yeah, pretty much. This one, what I do personally when I'm doing it is I draw a line through it, and I think, okay, that's positive, that's negative. So it's going from positive, which is increasing, to negative, which is decreasing. So that has to be a maximum. Does that make sense? Okay, positive derivative, which means above the x-axis. So it's positive because on this side it's above the x-axis. It means an increasing graph. That's what it means. A positive derivative means increasing. So my graph, my actual graph, must be increasing there. On the other side, it's below the x-axis, so it's decreasing, so it must be decreasing there. Well, if my graph is going from increasing to decreasing, there must be a maximum. That's what happens. If you're going from increasing into decreasing, you're going to have a maximum. Okay, now on the other one at 6, what's happening on the left side of 6? Is the graph positive or negative? Negative, because it's down here. And then on the other side, it's positive. So that means my original graph, f, is going from decreasing to increasing. So what's happening there is must be a minimum. Okay. Now, what Conrad talked about is really important, too, is that we don't necessarily know what's happening at endpoints. It's hard to say, if you're just looking at a graph of a derivative, it's hard to say if that, like this minimum, yeah, it's a minimum, but it's hard to know if it's the absolute minimum, which means it's the lowest ever point. Because an endpoint could also be a minimum or a maximum, and we can't really tell looking at it which would be lower without being given the original graph. So there are always minimums and maximums at endpoints. For instance, this one, okay, even though it's definitely not an absolute maximum, at 7 here, that would be considered a relative maximum because it's the highest point around it. Like if it goes a little to the left, it's lower, right? Like we're increasing at that point. So it's considered a relative maximum, but it definitely wouldn't be an absolute maximum. Whereas at 0, at time 0, that looks like the same level as day 6. So it's hard to say on that one, but it would be good. Now it's talking about point C. And you're just supposed to mention that C prime is a 0. And then it says it's tempting to say it rains right up until the beginning of the second day. That overlooks the fact about rainwater. That's important in flood control. I'm sure people had something interesting to say here. Okay. So here, what we're supposed to say, does anyone have an idea of what you're supposed to say? The runoff, yeah. It probably stopped raining before the second day, but water's just continuing to pour into the ditch because that's what water does. Not a calculus-related question, okay? You should be starting to feel more comfortable looking at graphs and making some comments about them in terms of the derivative. Now, we're going to kind of go a little bit out of order because I want to cover power rule today. So we're going to look at continuity and stuff tomorrow. Okay, we're going to skip to the slide that says derivatives on the calculator for right now. So I'm not sure what number it is. 28. Thank you, Haley. Okay, so your calculator is capable of computing a numerical derivative. That means like a derivative at a specific number, not to create the equation for it. So you should know how to do that because it's really easy. I've shown some of you already actually. If you hit math, it's the 8th option. That's not a good question.
That's pretty crazy formula.
Yeah, so you hit math and you use number 8. Okay, and I think everybody has a newish calculator, so something that looks like this is going to come up. Okay, something like that. And you just fill in the template. What you fill in is you fill in x here, you fill in the equation here, so x cubed, and you fill in your value down here, so 2. Okay, and it'll just spit out the derivative at that value. So here it would be 12, I think. Okay, can someone try it and check that I'm right? It is? Okay.
So you always put an X?
Yeah.
On that bottom one?
Yeah, just always use X. You could technically put a different letter and then use a different letter in your thing, but don't. Okay, is everyone good with this? Okay, I'm not going to do it anymore because that's it. That's how you do it, and I'm done with it now. Okay, you just need to know how to do it. It's not hard, and it's not something that you're going to have to do a lot of, but it can help you check your answers. Okay, so we're going to look, I'm not doing this one. We're going to look at a few rules of differentiability. Mostly I want to get to the power rule, so it will be really fun. We're skipping a couple slides here. This, first of all, is the constant rule. Okay, so this is a pretty important rule. It states that the derivative of a constant is 0. So, for instance, if I tell you that f of x is 3, then f prime of x is 0. Now, graphically, that makes a lot of sense, right? Because what does f of x equals 3 look like on a graph? It's a straight horizontal line through 3. It's not really enough. A lot of you guys really like to do this. You're like, it's a straight line. Sure is. Okay, but that actually is not an important factor of what y equals 3 looks like. The important thing is that it's horizontal. Any line that you could draw with a ruler is straight. So all linear graphs are straight. We're talking about it's a horizontal line. So the derivative is the slope of that line. What's the slope of a horizontal line? 0. So it makes a lot of sense graphically why the derivative of any constant is 0. The actual proof of it that I think is in your notes, is it there? Yeah, it is. Okay, so it's there, but let me show it to you just by hand. The actual proof is by using that definition. So the definition is the limit as h approaches 0 of f of x plus h minus f of x over h, right? Now, if it's a constant, like any constant, like f of x equals c, if you don't have anything to plug f of x into, or x into, so you don't have anything to plug it in. So f of x plus h is still just going to be c, whatever the constant is. F of x is also going to be c over h. So we end up getting 0 over 0, and we end up getting 0. Okay, so that's why. That's just kind of like the proof of it. But you just have to memorize it. So the Conrad?
Our notes say something different.
Oh, well, it's the same concept, though. It uses f of x minus f of a.
Yeah, it's the f of x plus f of a.
Yeah, so it's the same concept, though. You still end up with 0. Like, that's why. So
you need to be able to write this.
you would never have to do that. Okay, I would never ask you to actually prove it. This is just a pretty simple proof, so it's good to look at. You would never have to do the proof. But just so you know, so any derivative of any constant number, so like the derivative of pi, that one, like sometimes I put it on a test and it like half the class gets it wrong because they're like, I don't know, what's the rule for pi? Pi is a constant, so the derivative of it is 0. Okay, the derivative of any constant is 0 all the time. So that's a rule to follow. Now, this is probably the most important derivative rule that you will see. Okay, and it's probably going to, I don't know, usually it makes people angry when they first learn it. It's that if you're taking the derivative of something to the power of n, so x to the power of n, where n is just an integer, the derivative is n times x to the power of n minus 1. So there's quite a long proof there, and I don't really particularly want to go over it with you, to be honest. But I'll just show you kind of how this works. So there is an example there, d over dx, which means derivative, remember, of x cubed. So here's how this rule works, because it looks complicated when you see it written down like this at first, but it's actually not that complicated. What you do is you take the power, the exponent, so it's a 3, and you put it out front. Okay, then it's to the power, it's x, so we keep the x, and the new power becomes n minus 1, which is 3 minus 1, which is 2. So the derivative of x cubed is 3x squared. Now let's just check that.
So you don't do anything with the d over dx?
No, that means take the derivative. That's what that means.
Oh.
Okay? So if I use the definition of a derivative, I'd have to do x plus h cubed minus x cubed over h. And if I expanded all that, I would end up with x cubed plus 3xh plus 3... actually, no, wait a minute. I guess I should do it all the way out. Oh yeah, 3x squared h plus 3xh squared plus h cubed minus x cubed all over h. The x's cancel. We end up with our h being factored out. So we get 3x squared plus 3xh plus h squared over h. The h's cancel. We plug 0 in for h and we get 3x squared, which is shockingly the same as that. Okay? So this is a slightly faster way of taking a derivative. Okay? You don't need to use the definition of derivatives anymore. Okay? You won't have to use it again until the test. Okay?
So if it's like x cubed plus x squared plus x.
Yeah, let's look at something like that.
X squared.
Yeah, so let's do one like, let's just do the one that Ryan just said. So you said x cubed plus x squared plus x, okay? So all I would do is I would drop the 3 down, so that's 3x, and then it's 1 less. So now it's x squared, plus, I drop the 2 down, so now it's 2x, and it's 1 less, so it's 1.
Wait, where do you get that?
Which from the power?
It's the rule. So the 3 falls down, becomes the coefficient, and the power is 1 less. Okay, then the 2 falls down, so the 2 comes down to be the coefficient, and now the power is 1, but I wouldn't write it. Now, does anyone have an idea of what the derivative of x would be? It is 1, yeah. Okay, it's 1, because the power was 1, and it falls down, and now it would have a power of 0, which just means no x, so it's just 1. And that's the derivative of that. The definition of derivatives would probably take you, I don't know, 10 minutes to do that.
And that usually makes people mad.
Yeah, because it's so much easier. You've been doing all those limits? What a joke. Like, I could do them in my head looking at them. Okay, anyway, let's look at one with some coefficients. It's pretty funny.
That was the whole wasted unit.
Yep,
So this will pass. We don't have to do that other stuff like ever again.
until the test.
So like today?
Okay.
I'm still gonna do
Huh?
it if I have to do it in the test, just for practice.
No, you can't do that. Okay, so let's do this one. So if you have 5x squared, this one's a little trickier because there's a 5 there. Does anyone have an idea of what the derivative of 5x squared would be? 10x. The derivative of 4x. It is 4. Well done. And the derivative of negative 8? 0. So there we go. It's 10x plus 4. You guys have actually done a lot of these, and none of you noticed the pattern. So, but it does come back to what Clayton said on Thursday when he asked, is the derivative of something always a degree less? This is the reason why it's always a degree less. Because if you have a cubic, the cube's going to fall down and become a squared. Okay? So it is related to that. But anyway, this is how you do them. They're very easy. Let's do some harder ones, though. Well, they're not going to be forever. Oh, yeah. So I'm not even going to do an example here, but the sum and difference rule just states that when you're adding up, when there's two things adding, you just do the derivative of each one. So like what we just saw, where you have the derivative of something like 2x to the power of 3 plus 5x, that you can just do it as separate ones. So you can just do that separately so that you get 6x squared plus 5. That's all this is saying, okay, that you're allowed to do them like one at a time. So you don't really need to worry about the rule. It's not a complicated. Okay, and then let's look at some hard ones here. Okay, so these ones are harder, obviously. Okay, so this first one's actually not really particularly hard. If we're asked here to find this one, all I do, the numbers are high, but there's not really anything really difficult. But imagine if you were trying to do the definition of a derivative here, you literally wouldn't be able to. Or I mean, I guess you could, but it would take you like years, because you'd have to expand x plus h to the 100, which, I don't know, someone could devote their life to that, probably. So what you do is you drop down the 100, so what will my coefficient be for f prime? 1500. They multiply. The new power will be 99. Okay, now 3x to the power of 12, what will be the coefficient? 36, and it'll be x to the power of 11. Okay, I'm just going to write underneath plus, oh actually no I won't because there's only one thing left, plus 5. Okay, and that's it. Pretty easy.
One might be less.
And then what about the 40?
What if it's a negative 40?
Okay, guys, be nice to each other, Haley.
You said Haley?
Yes. You did too. You threatened Conrad.
Okay, why she usually does, she didn't today. She usually does. Ryan threatened me.
Was it? I don't know. He sounded just like Haley. No, I don't think that's what I meant. Okay. Here, y. Now this one that you see here it's important to rewrite it differently. So we have 8z squared minus 1 over 3z to the power of 5 plus z minus 23. Now obviously the problem that I would expect most people to come to is the 1 over 3z to the power of 5. You should write it differently. So 1 over 3 times z to the power of 5. Does anyone have an idea of how to write that a little differently?
3 z to the power of 5 to the power of negative 1.
To the negative 5. That's really what you want to do. So keep the 1/3. So the 1/3, keep it. But if you have an exponent that's down in the denominator, all you do is you bring the variable up and you make it negative. Okay, so we're on the right track. Now everything else can stay the same. So y prime there, if I'm taking y prime, that's 8 times 3 is 24. Z squared. Now here what I would do is I'd bring the negative 5 down, so it's going to become positive 5/3, because 5 times a third is 5/3. Okay, pretty complicated math. And now it's really important that you continue to follow the rule, because what I see happen is people are like, well, it's one less, so it's going to be z to the negative 4. But that's not true. Lower than negative 5 is negative 6. And you can either write z to the negative 6, or you could put the z on the bottom. But let's just for now write z to the negative 6. What's going to be the derivative of z? 1. Now I would prefer your answer be written without any negative exponents, because in math, generally speaking, negative exponents are kind of considered not cool. So we put 3z to the power of 6 on the bottom plus 1. You would expect to, even if you didn't put this in your answer, I'd probably mark it right. I'm fine, like whatever, it's fine. But you would expect on a multiple choice question for the answer to be written this way. Okay, the answer would be written without any negative exponents. So you should be pretty comfortable moving negatives or moving exponents from the bottom, from the denominator up to the top, and marking it as negative. Are people okay with that? Okay, that's not too bad. Now this last one obviously looks a little worse. Okay, now this one again, what you'd want to just do first is rewrite it with powers instead of roots. So instead of the square root of x, what is that as a power? 1/2. So it's x to the power of 1/2. This one, 9 to the power, or 9 times the cube root of x to the power of 7 is x to the power of 7/3. Okay? And finally, minus 2 to x to the power of, does anyone have an idea of what that exponent would be? Close. Negative 2 over 5. Okay, so it's always the number that's inside is the power, the index, the number that's like the cube root or the fifth root is the denominator. Okay, so it's just, I know it's hard to read there, or I'll maybe make it bigger, and maybe I should write it in black. It's not really easy to read. This will probably make it much easier. I know. 7/3 minus 2x to the negative 2/5. It's negative because it was in the denominator. Okay, so now let's try doing the derivative of this thing. So I drop down the half, so I have half x. Now what's 1 less than a half? Negative a half. Plus, now what's 9 times 7/3? It is a whole number. He typed it into a calculator. Yeah, you should divide it and then times it, probably would be easier. 9 divided by 3 is 3, times 7 is 21. That's what you should be doing in your head. Then what's 1 less than 7/3? 4 over 3. Okay, so these kind of things with fractions you should be able to do. So 1 less than 7/3, a whole is 3/3. So you're taking away 3/3 from 7/3. So you get 4/3. You need to practice doing this without a calculator, or you're not going to be able to do it on a test. The other way you could have done 9 times 7/3 is what Ryan said. You could do 9 times 7 is 63 divided by 3 is 21. You could do that. It's just a little longer than realizing that you could do the division first. Okay? Then here, if we take down the 2/5, I'm going to have negative 2 times negative 2/5. So what's that going to be? Positive 4/5. Okay, it's positive 4/5 because 2/5 doubled is 4/5. Okay, some of this stuff is just things you should be thinking about logically. If you had two groups of 2/5, you would have 4/5. Okay, and it's a negative times a negative, so it's a positive. Then if we go 1 less than negative 2/5, so a whole is 5/5. So if we subtract 5/5 from negative 2/5, negative 7 over 5. This will be slow going at first, but the more you do it, the better you are at it. The reason I'm good at it is because I've done it a lot. Now, if you are wanting to be like my really good books, you would rewrite this so it looks nicer. Either with roots or with fractions is kind of fine. I mean, like especially when it's a half, like writing it as a root is kind of nice, but not necessary. However, really trying to get rid of the negative fraction, the negative powers is a good idea. So that's 1 over 2x to the half, or you could write it as 1 over 2 root x. They'd both be good. Plus 21x to the 4/3 plus 4 over 5x to the 7/5, like that. Okay, or you could write them all as roots if you wanted to. Okay, so if you wanted to write them all as roots, it would look like 1 over 2 root x plus 21, cube root x to the power of 4 plus 4 over 5 fifth root x to the power of 7, like that. Okay, but I very rarely would turn something into something with roots because they're not usually very useful. So I'd probably personally use this answer. Okay. But if you wanted to, you always can. It's up to you. Okay, so if you're given something like this, find the equation of the tangent line at x equals 16. What you would do is first find the derivative. So if I go f prime here, would be 4 minus, and this, and I just personally, like if I'm doing it, I don't know, I just kind of write, I'm like, that's x, ooh, whoops, that's 8x to the half. I just remind myself of that. So if I drop down the half, it would become 4x. What's 1 less than a half again? Negative a half. Now, this is why it's really important to know how to manipulate these, because if I just tried to plug in 16 into that, it would be hard, because I'd have 16 to the power of negative a half. And most people would look at that and be like, I don't know what that means. So instead, if you rewrite this as 4 minus 4 over x to the half, or root x, it becomes much easier to see what you'll get when you plug in 16. Because I get 4 minus 4 over root 16, which is 4 minus 1. So that's 3. Okay, so f prime of 16 is 3. What does that 3 represent? The slope. So what you should be using is the m x minus x1 plus y1, and that 3 is the m value. x1 is 16. What's y1? Put it in the original. So f of 16, so it'd be 4 times 16, which is 64, minus 32, so it's 32. Okay, and people, that's the kind of thing that people would be like, I have to be able to do that by hand? And it's like, yes, it's not that hard. Takes like half a second. Okay, so you do it that way. This is the answer. Okay, so that is